As the calendar turns to October 29th, 3i Atlas will disappear from view behind our star, precisely when Avi Loeb suggests this colossal, high-velocity interstellar wanderer might perform an unobserved pivot that binds it to our solar neighborhood permanently. The conventional explanation labels it a passing comet, but the preliminary observations challenge that narrative. A core, perhaps 20 kilometers in diameter, tipping the scales at over 33 billion metric tons, yet displaying virtually no non-gravitational thrust despite violent gas eruptions. Should Loeb's hypothesis prove accurate, humanity might be observing the inaugural interstellar traveler to settle among us, and surveillance will be impossible during the crucial instant. What eludes detection throughout that solar eclipse, and whose interpretation will triumph when Atlas re-emerges? October 29th marks an inflexible boundary on the timeline. That date sees 3i Atlas entering the brilliant zone behind our star, severing access for every Earth-stationed instrument. The celestial mechanics are unyielding. Earth, our star, and the Wanderer aligned perfectly straight, with our world positioned on the inferior side of the radiance. Throughout nearly 6 weeks, the heftiest interstellar body ever identified will travel invisible, its trajectory and potential alterations concealed from immediate observation. This eclipse transcends mere logistical nuisance. It indicates that the pivotal episodes, perihelion, the tightest solar proximity, and any prospective orbital adjustment, will transpire outside our observational capacity. The span between Earth and our star measures roughly 150 million kilometers. During alignment, Atlas travels slightly farther at 1.36 astronomical units. No terrestrial facility can distinguish its dim radiance from the stellar inferno. Even orbital instruments like Hubble and JWST must postpone operations, their protection systems activated by dangers of solar pointing. The tangible consequence: an information void extending from late October into early December. Position tracking, wavelength studies, even fundamental luminosity readings all cease. The sole prospect for observation depends on select solar monitors and coronagraphs, instruments designed for solar weather study, not remote comets. Their capability and capture frequency scarcely detect targets as dim as Atlas. For the majority of researchers, the aperture closes exactly as the narrative's most vital segment commences. Every inquiry regarding natural departure or deliberate retention, regarding comet or construction, remains frozen in this imposed quiet. Time advances, and the decisive instant will unfold where observation proves impossible. Avi Loeb's focus sharpened immediately when preliminary brightness data arrived. The opening dimensions for 3i Atlas, 20 kilometers wide, struck like thunder. To establish perspective, 1i Oumuamua spanned less than 1/4 kilometer. 2i Borisov, the prior interstellar comet, extended roughly 1 kilometer across. Atlas, comparatively, exceeded anything detection programs anticipated discovering initially by a full magnitude. The figure wasn't speculative. It derived from the body's luminosity, adjusted for range and solar positioning, then calculated against established cometary reflectance. Given a magnitude significantly exceeding 12 and no indication of thick, light-blocking envelopes artificially inflating measurements, the inference was unavoidable. The core demanded massive proportions. Loeb's doubt emerged from calculations. Detection predictions indicate that for each substantial interstellar arrival, thousands of tinier, dimmer ones ought to have appeared previously. The Atlas program, alongside Pan-STARRS and Vera Rubin, surveys celestial regions nightly, calibrated to identify precisely these rapid, sun-directed targets. Still, the initial 2 interstellar finds were modest, and abruptly, a behemoth materializes. The probability, under any distribution framework, defies credulity. If dimensional assessments prove sound, either detection systems have overlooked a tremendous population of smaller specimens, or something exceptional and unaccounted operates. Here, Loeb's reasoning commences. A 20-kilometer interstellar specimen, emerging so quickly after the first pair, violates the power law predictions that support contemporary detection methodology. The statistical warning signals activated not from Atlas's brightness, but because its extraordinary magnitude contradicted everything researchers believed existed beyond. For Loeb, that solitary measurement, 20 kilometers, established the primary and most conspicuous irregularity in an expanding catalog. A mass exceeding 33 billion metric tons now positions 3i Atlas in historical records. This value, extracted from motion modeling and the comet's sustained luminosity, overshadows every verified interstellar predecessor. Yet the contradiction starts precisely here. Despite robust degassing rates, approaching 100 to 150 kilograms each second, primarily carbon dioxide, no detectable non-gravitational thrust exists. In cometary research, this represents the archetypal propulsion dilemma. Outgassing functions as maneuvering jets, nudging the core incrementally from its calculated course. For standard comets, even moderate activity produces a signature in positional archives. A gradual displacement, a delicate bend away from gravitational prediction. However, the Minor Planet Center's worldwide collection, encompassing over 4,000 location records, discovers no such departure for Atlas. The ceiling on its non-gravitational thrust remains under 15 meters per day squared, sufficiently minimal that, given its documented activity, only an authentically massive specimen could stay so unperturbed. The figures intensify the paradox. Calculate the recorded gas output, factor the ejection speed, and partition by approximated mass. The anticipated reactive thrust ought to manifest in records, unless the core proves not merely large, but exceptionally compact, or the degassing achieves perfect omnidirectional equilibrium. Monte Carlo modeling explores every reasonable pairing of core dimensions and compactness for anything under approximately 5 kilometers diameter, or below 1,000 kilograms per cubic meter density. The mathematics collapse. Outgassing would have deflected Atlas from predicted motion long previously. Solely a massive consolidated structure satisfies both brightness and motion evidence. Competing explanations, such as jets discharging in exact counterbalance, or a cluster of weakly connected pieces, demand precision physics and unlikely configuration. The prevailing framework struggles reconciling figures without invoking chance anomalies or selective reasoning. For Loeb and Associates, this transcends mere interest. It constitutes an explicit challenge. If mass proves genuine and thrust remains absent, the pathway toward non-natural possibilities stays accessible. Detection methodology depends on volume, considerable volume. For every giant like 3I Atlas, distribution frameworks anticipate skies teeming with thousands of tinier, dimmer interstellar drifters. The reasoning seems straightforward. Smaller specimens vastly outnumber larger ones across every documented asteroid and comet reservoir. If discovery infrastructure functions properly, inaugural interstellar detections should capture the smallest, those outnumbering giants exponentially. Yet the historical record contradicts expectations. The Pan-STARRS system, the Atlas Grid, and currently the Vera Rubin Observatory have monitored skies for years, cataloging millions of contacts. Their capability has advanced where specimens merely dozens of meters across, if traveling sufficiently fast, would register. The initial two interstellar discoveries, Oumuamua and Borisov, aligned with predictions. Both proved small, dim, and precisely at detection thresholds. Subsequently, without forewarning, Atlas manifests. 20 kilometers broad, exceeding 33 billion metric tons, radiating far beyond sensitivity limits. No accompanying swarm of lesser relatives, no incremental size progression, merely a statistical anomaly. Distribution specialists performed calculations. If 3I Atlas represents typical specimens, detection programs should have identified hundreds, potentially thousands of inferior specimens presently. Instead, the tally stands at 3. Researchers at Pan-STARRS and Rubin documented the discrepancy in internal communications, cautioning that probabilities of discovering giants before smaller counterparts prove astronomically improbable, under 1 in 10,000 by certain assessments. The power law, foundation of dimensional distribution, appears violated. Either the cosmos conceals an enormous population of dim, elusive specimens, or Atlas constitutes an outlier challenging every projection. For those monitoring irregularities, this transcends curiosity. It signals that something foundational in the statistics proves incorrect, and that 3I Atlas's narrative already reconstructs established principles. Trajectory charts for 3I Atlas display a route closely following the solar system's ecliptic surface, inclined merely 5 degrees approximately. For an entity approaching from interstellar distances, this configuration proves far from typical. Most documented comets and asteroids, including those originating within our system, pursue orbits that incline and rotate throughout the solar vicinity. A random arrival from beyond should penetrate its steep inclination, its course molded by remote stellar chaos. Instead, Atlas advances nearly parallel to planetary geometry, navigating a passage typically occupied by indigenous specimens. The configuration grows more peculiar under scrutiny. Throughout weeks preceding perihelion, Atlas completes a succession of planetary proximities with major worlds. On October 3rd, it passes within 29 million kilometers of Mars, a separation that, by interplanetary measures, qualifies as extremely close. The progression continues. Subsequently, its route carries it within critical range of both Venus and Jupiter, accumulating a series of planetary approaches seldom witnessed outside deliberately calculated space operations. Orbital specialists process calculations and determine the accumulated likelihood of such a massive, rapid specimen threading this exact route proves infinitesimally small. For individual planets, proximity probability remains low. For 3 consecutive encounters, probability plummets below 1 in 1,000. This configuration transcends mere curiosity. The ecliptic hugging route positions Atlas optimally for gravitational influences. Each planetary approach could theoretically adjust its velocity or modify its course. However, genuine intrigue emerges from how these accumulated encounters establish perihelion conditions. The trajectory appears precision-calibrated, nearly as though engineered to optimize possibilities for dramatic maneuvering near our star. For those examining boundaries between natural and deliberate, the flight route itself emerges as silent testimony, provoking questions that calculations alone cannot resolve. Initial imagery of 3I Atlas troubled observatory personnel. Rather than anticipated tail formations, a concentrated forward luminosity dominated the sunward aspect, a brightness resisting every adjustment for motion blur or equipment anomaly. Imaging specialists at Gemini South and the VLT examined records, seeking technical clarification, but the asymmetry persisted. As the comet approached the sun closer, the luminosity diminished and a conventional tail commenced extending backward, conforming to solar wind. Some interpreted this as geometric illusion, others as indication of genuine transformation, possibly surface breaking or abrupt activity from interior layers. Spectroscopy teams redirected attention toward the comet's composition. JWST's NIR spec, during a brief interval before solar alignment, recorded a volatile proportion defying predictions. Carbon dioxide exceeded water by approximately 8-to-1. For solar system comets, water typically dominates volatile composition. This proportion suggested a core either maintained in profound freeze since interstellar transit or blanketed in carbon dioxide ice layers. Calibration personnel recommended prudence, designating results as preliminary until additional observations could validate or dispute findings. Hypotheses proliferated. Some indicated a carbon dioxide shell protecting water-abundant depths. Others suggested possible contamination or computational error. The discussion expanded into extended digital exchanges, with every team advocating their interpretation. Subsequently, during late September, an abrupt increase of green radiation pervaded the envelope. Both recreational and professional observers documented the transition, attributing it to C2 or CN molecules fluorescing beneath solar ultraviolet. For typical comets, green manifests near perihelion, but here it emerged prematurely and intensely, exceeding forecasts. The chromatic shift prompted fresh inquiries regarding volatile ice stratification and the comet's surface composition. Each irregularity, optical, compositional, chromatic, layered ambiguity upon ambiguity. With the comet disappearing behind our star, resolutions must await, leaving its authentic character suspended between construction and disclosure. Avi Loeb's argument depends on an interval so compressed, it scarcely registers cosmically. At perihelion, October 29th, 3I Atlas will travel at approximately 44 kilometers per second, an interstellar projectile sweeping just 1.36 astronomical units from our star. For any specimen on hyperbolic trajectory, this constitutes the singular instant where a solitary impulse, a velocity modification of merely several kilometers per second, could shift equilibrium from departure to retention. The mechanics prove inflexible. To transition from outbound interstellar trajectory into gravitationally bound solar orbit, Atlas requires a delta V roughly 8 kilometers per second, executed at closest approach instant. Anything insufficient, and the comet continues outward permanently. This operation, if executed, becomes invisible. Solar radiance blinds every terrestrial instrument. Even superior orbital coronagraphs will struggle identifying a dim, rapid moving point against solar backdrop. Detection thresholds for these systems remain around magnitude 8 to 10, excessively bright for a comet like Atlas during solar alignment. The practical result: any trajectory modification, any activity surge, or engineered propulsion would pass undetected until the comet reappears weeks afterward. The Mars encounter, merely 29 million kilometers distant on October 3rd, presented brief possibility for direct imaging. High-rise operators considered feasibility, executing calculations on angular dimensions and apparent luminosity. The mathematics eliminated opportunity. At that separation, a 20-kilometer specimen subtends under 0.15 arcseconds, smaller than high-rise's diffraction boundary, even as point radiation. Atlas would prove excessively dim for detection. No surface characteristics, no jets, no probe deployments. The most capable camera orbiting Mars can solely observe emptiness. For Loeb and advocates, this enforced invisibility constitutes both obstacle and prospect. If an operation attempts execution, the proof will inscribe itself into the comet's orbit, awaiting interpretation when Atlas returns to visibility. Tom Statler, NASA's principal small-body researcher, establishes a definitive position. It appears cometary. It performs cometary functions. It overwhelmingly resembles in virtually every characteristic the comets familiar to us. That establishes the foundation. The prevailing perspective maintains that 3I Atlas conforms, albeit awkwardly, within the broad, chaotic family of natural comets. Unusual mass, statistical aberration, strange composition. Comets prove unpredictable, trajectory, peculiarities, and planetary proximities. Coincidence amplified by cosmic vastness. Researchers like Karen Meach and Quan Yi reinforce this position, referencing selection biases, incomplete survey coverage, and unpredictable conduct of volatile-rich specimens. For them, extraordinary claims demand extraordinary substantiation. Avi Loeb examines identical observations from opposing perspectives. He avoids formal scoring, but his reasoning accumulates irregularities. Mass, dimensions, ecliptic conformity, planetary encounters, composition. The more these characteristics converge, the stronger justification for heightened scrutiny. In Loeb's perspective, when sufficient oddities accumulate, the exclusively responsible action maximizes observation. Particularly when exceptional circumstances, like perihelion behind our star, could mask a defining operation. He never quantifies explicitly, but the philosophy remains elementary. If the irregularity catalog lengthens, treat the specimen as though consequences prove significant. The subsequent critical interval commences early December, when Atlas reappears from solar alignment. Every major facility will prepare checking for orbital modifications, rotation changes, and spectral variations. By March 2026, as Atlas approaches Jupiter, a secondary observation round will assess whether its course maintains hyperbolicity or if transformation occurred. The evaluation framework avoids scoring irregularities. It concerns tracking tangible, testable forecasts. If the orbit maintains trajectory, the natural framework prevails. If deviation occurs, the discussion enters fresh territory. Presently, the singular certainty remains that the narrative depends on revelations when the eclipse concludes. On October 29, 2025, 3I Atlas will transit behind our star, eliminating all Earth-stationed observation at the exact instant Avi Loeb proposes a reverse Oberth operation could secure it within our solar system. The specimen's estimated 20-kilometer dimensions and mass exceeding 33 billion metric tons, combined with negligible non-gravitational thrust and a carbon dioxide to water proportion approaching 8 to 1, challenge expectations for natural interstellar comets. Nevertheless, as of this moment, no concrete proof validates any artificial genesis. NASA's formal stance maintains that comets can display unpredictable characteristics and numerous questions, such as the origin of its green spectral episode and the authentic nature of its trajectory, remain unresolved. When Atlas reappears in December, its revised orbital parameters and compositional signatures will furnish the ultimate evaluation. Until that moment, The sole certainty involves rigorous observation requirements and transparent scientific discourse.